help you, but this is a great thing to bring up at parties.
Okay.
Okay, and it's a classic probability problem. If you go down and buy a probability book, it would probably all start with this problem. So let me give you the problem and I'll blow your mind. That's why it's a good party problem. You walk into a house where the family has 2 children. You walk in and you see a boy sitting on the couch. What's the odds that the other child is a boy?
1/2?
No. 1 out of 3. Here's the way the logic goes. 2 children can be born, boy, boy, girl, girl. The girl could be born first and then the boy, or the boy could be born first and then the girl. Well, when you walk into the house and you see a boy, you've eliminated that possibility. Of the 3 equal possibilities that remain, only one of them has the other child as being a boy. Therefore, the odds are 1/3. Shocking. Now, I'm going to shock you even further. You walk into the same house and the parent says, "Meet my oldest child," and it's a boy. Now, that changes the odds on the other one being a boy. Because the parent has told you that it's the oldest child, you can cross that one out, and you can also cross that one out. There's no way a girl was born first if you're looking at a boy and they told you the boy was the oldest child. So now there's only 2 possible ways they could have been born. And of those 2 ways, only one of them has a boy as the other child. So the odds are 1/2 if you know you're looking at the older or younger sibling. But the odds are 1/3 if you don't know that. Now, you want to start some arguments? Bring this problem up amongst any group of people. We were having a DVD night a few years back with my dad, and all my relatives were there. And they're all scientists and college graduates, and there were like 13 people in the room. And I brought this problem up. I could not get a single other person to agree with me. And I got a math degree from Colorado School of Mines. But nobody would believe me. Nobody. Even when I told them, you can go to Google and Google this problem, and they'll give it to you. But all probability books have this problem in it. Because it's called a problem of restricted choice. And that's why the odds change depending on whether you know the child is the younger or
Christy,
the relative age of the child. But most people are absolutely shocked by the answer of 1/3 to the first question. And they're even more shocked by the answer of 1/2 if you happen to know the child is the oldest or the youngest child. It's counterintuitive. It doesn't make a lot of sense. And it doesn't make a lot of sense that the probabilities would be different just by knowing that additional piece of information. But they are. Trust me. So that's the only fun probability problem I know. That's really fun. I mean, that truly is fun. You'll make conversation for an hour with anybody you bring this up to.
Yeah.
But make sure you understand it, because you don't want to bring it up to somebody if you can't explain it. And the explanation has to do with these 4 possible ways that children can be born. 2 kids can only be born in this possible manner. There's 4 ways that 2 kids can be born. That's it. All right. What's the odds of flipping a coin and flipping heads 3 times in a row? What's the odds of flipping heads on the first toss?
1/2.
What's the odds of flipping heads on the second toss? Both of them have to happen. And the odds of flipping heads on the third toss, they're all 1/2. Whenever you flip a coin, it's always 50-50 that you're going to flip heads or tails. And there's no dependence between your first flip and your second flip. In other words, the odds on the second flip are exactly the same as the odds on the first flip are exactly the same as the odds on the 209th flip. In other words, when you flip a coin, it's an independent event. So all 3 have to happen, so you have to multiply it, so it's 1/8. 1 chance out of 8 that you'll flip it 3 heads in a row. It's also 1 chance out of 8 that you'll flip 3 tails in a row. But whenever multiple events have to all happen, then you multiply. Now, if the odds of it raining on any given day are 1/10, then what are the odds that it'll rain tomorrow and the next day, both?
1,000th.
Well, 1/10 times 1/10, which is 1/100th. However, this problem isn't quite the same. And the reason is that the odds of it raining tomorrow might be 1/10. But if it actually rains tomorrow, that changes the odds of it raining the next day, because it means we're in the middle of a storm. So these are not independent events. These are actually dependent events. So it's never going to be 1/10 times 1/10 when you're talking about raining or snowing. Because if it actually did snow tomorrow, or rain rather, then the odds are going to be better than 1/10. It'll rain the following day. So one of the biggest difficulties with probability is determining whether events are independent of one another or related. Now, when I was doing my boy-girl thing, that was based on the fact that any child born is 50-50 likely to be a boy or a girl. And in reality, that's not quite true. The odds of the second gender being the same as the first is actually slightly better than 50-50. In other words, if you're having children and you have a boy, the odds that you're going to have a boy with your second child are a little bit better than 50-50. So it's not completely independent events. But my entire analysis that I went through was based on the fact that they're all independent of one another. In other words, when I said the children could be born girl, girl, boy, boy, girl, boy, or boy, girl, each of those is 25% likely. All 4 of them. Because there's no dependency. We will ignore the dependency of having 2 kids of the same gender. Okay? Area problems are always kind of fun. We have a dartboard. It's got an inside circle that's got a radius of 3, and the outside circle has a radius of 8. If we throw a dart, and the dart is equally likely to land anywhere inside the big circle, what are the odds that it's going to land in the little circle? what this becomes is the area of the little circle divided by the area of the big circle. It's the area of the little circle.
9 pi.
It's the area of the big circle.
64 pi.
9/64 are the odds that your dart will land in that area. Because that area is 9/64 of the area of the total circle. And the dart can land anywhere randomly, since there's more area to land in the outside area. In other words, this area here, there's a lot more area to land in than there is the little circle. But the whole thing is predicated on areas and the ratio of areas. Do you have any probability problems that you can bring?
I don't actually.
Okay. You've gotten into dependent and independent, I believe.
Yeah.
If you have independent events, A and B, then the probability that both of them will happen is the probability of A times the probability of B. In other words, when I was talking about flipping a coin, and I was saying, well, if you wanted to flip heads, say twice in a row, well, the probability of A is 1/2, probability of B is 1/2. So the probability of picking 2 heads in a row would be 1/4. Now let's talk about dependent events. If you have dependent events, then the probability of A and B happening is the probability of A times the probability of B minus the probability of A given that B has already, no, B given that A has already happened. For example, if you're drawing from a 52 card deck, what's the probability of drawing the king of spades?
152. 1/52.
What's the probability of drawing a king? Let me put it like that.
4/52.
Okay, which is 1/13. What's the probability of drawing a king and a queen with your next pluck? Probability of drawing the queen, if you're dealing with a 52 card deck each time, is the same as probability of drawing to a king.
Yeah,
So it'd be 1/169. But now let me change the question and say, what's the probability of drawing a king? Do not put it back in the deck and then drawing a queen. Well, now the probability of drawing the king is 1/13. But now there's 4 queens and there's only
51 cards.
51 cards. So it's that, which is not the same as 1/169. I can't think of a problem that requires that formula. This was not it, but this does illustrate dependent events. In other words, the probability of B was not exactly the same as the probability of A, because the probability of B was a 51 card deck missing a king. So you have to recalculate the probability of B if it's without replacement. It's the way decks of cards are used a lot in probability teaching, as you've probably figured out.
Yeah, that and dice and coins.
Exactly. That, dice, and coins. Exactly. A gambler's paradise. All right. Why don't we call it a session here? I can't think of any other clever or good probability problems.
Yeah,
And
they're not overly hard.
it's just about 6:30, but no,
Yeah.
probability isn't really very hard. What's the probability of rolling a 2 on 2 dice? In other words,
Rolling a 2 on both dice?
well, rolling a 1 on both dice. In other words, the probability that the sum will be 2.
1/12.
No?
Or 1/36, sorry, 1/36.
136. Because you got to roll a 1 on the first dice. That's 1/6.
Gotta roll a
You
1 on the
got to
second
roll a
dice.
1 on the second dice. That's 1/6.
I added the denominators instead.
1 over 36. Always know that if it's an and,
You always multiply.
If it's an or, you add.
Okay.
In other words, if I'm talking the probability of A or B, let's say I want the probability of drawing a king or a queen, well, that's 1/13 plus 1/13, or 2/13. And you'll see that there are 8 kings or queens, so it's really 8 over 52, which is the same as 2/13.
Mm-hmm.
So whether it's and or makes a big difference.
Okay.
All right, Cole, next Monday?
Yes. I'll have to start doing later times, I think. Do you have a later time on Monday?
Yeah, here, let me pull my
'Cause
calendar
I can't
up and I'll have
do
a
anything until after like 5:30 or so.
When do you want it? I can move it to wherever you want.
Probably 6 o'clock works great.
For all time or just next month?
Just for the next like month or so, because I'm in the spring play, and so
Okay.
we have rehearsal until 5 o'clock every day. So
Okay. I will go through the next 4 sessions and move them all to 6 o'clock.
awesome. Thank you very much.
You're welcome. Bye-bye.
Bye bye.